So today we are going to discuss three questions. In these three questions, we have two from year 1997. So there are two questions from 1997 and we have one question from 1996. So in the first question, which was asked in the 1997, it states that three infinitely long thin wires, each carrying current I in the same direction, are in the xy plane of a gravity-free space. The central wire is along y-axis, while other two wires are along x plus minus d. So based on this, we have two questions. In part A, find the locus of point for which the magnetic field B is 0. If the central wire is displaced along the z direction by a small amount and released, show that it will execute a simple harmonic motion. If the linear density of the wire is lambda, find the frequency of oscillations. So we are given three wires. So let me draw a approximate figure for that. So we have a x-axis and we have a y-axis. Three wires are given to us. So one wire is along this y-axis, and let us suppose this is our origin O. Another wire is to left of it at a distance of d. Okay. So this is our x is equal to minus of d, and the third wire is to right of at the same distance, that is at x equal to d. So it means both the wires are equidistant from the center wire. So these are three wires, and it said they carry the current in the same direction, and they carry a current of I in the same direction. In the first part, we have to find out the locus of point in which the magnetic field is 0. So we have to find out the region basically where the magnetic field is 0. So let us divide this entire schematic into the regions. This we have a region 1, region 2, region 3, and we have a region 4. And that's all is given to us. So we have the region, total 4 regions are there. X-axis is divided into 4 regions, and we have our region 1, which is for x is less than of minus t. Then we have region 2, and that is for minus t, x greater than minus t but less than 0. And we have region 3. Region 3 is for x greater than 0 but less than d. And finally we have region 4, and it is for x greater than d. Okay. So let us try to find out what will be the magnetic field, or we can say we can make a rough estimate about the magnetic field, whether it will be 0 or whether it will not be equal to 0. So let us start with our region 1. Which is x less than minus t. And so from here we can draw one important conclusion, that all 3 wires lie to the right of the point, lie to right of the point. So we can say that the magnetic field at the left of the wire will be our out of the page. Okay. For using, you can say by using the right hand rule, you can say the magnetic field at left of a wire is out of the page, or we can say along plus z axis, and the direction of current in all the 3 wires is same. Therefore we can say the all 3 wires will create a field in z direction, plus z direction rather. The direction of current is same, so the 3 wires creates fields in plus z direction. So it means they are going to all add up. You can see all fields add up in same direction. All fields add up in same direction. They will be minus z, not plus z, my mistake. Minus z as well as minus z. Okay. Because the current is in upward direction, so the field will be in along z axis. 1 second. Let me, this is x axis, y axis, and this is z axis. Yeah, so this looks good. So it will be our plus z axis, and we can just represent it with a dot. This is our z axis. So all the fields add up in same direction, and therefore we can say no field in the region is x less than minus d. That's why it's plus z, my mistake. Okay, I just, So now it's correct one, because the region is on the our less than minus d. So all the field add up in the same direction. So that's why we can say that non-zero magnetic field is not possible. Now we come to the our region 4. And for region 4, all wires lies to the left of the point. All wires lie to the left of the point. And region 4 is for our x greater than d. So similarly, the field is towards into the page. Therefore, we can say magnetic field at the right of a wire is into the page, that is minus z axis. So once again, all the wires will add up because of the same direction. All fields add up in same direction. And same direction means minus z axis. Therefore, magnetic field cannot be 0 in region 4. Now we come to region 2 and 3. Region 2 and 3, and our region 2 is x greater than minus t but less than 0, and in region 3 we have x less than d but greater than 0. Okay. So it means we can easily see that the point lies between the wire. Okay. Whatever point we take, it is going to lie within the wire. So we can say that the point lies between the wires. Therefore, some wires are to the left and some are to the right. Therefore, some wires are to the left and others are to the right, and others are to the right. That means some wire will have field along positive z axis while other is going to have in minus z axis. So it means that some wire produces field in plus z and others in minus z. So because of this we can draw a conclusion that cancellation is possible. Cancellation is possible. So let us do the calculation for region 3, and similar we can copy for the region 4 as well. So you can say for region 3, and our region 3 is for x less than d but greater than 0. Okay. So therefore, if we can draw the rough figure, and once again we have a x-axis and we have a middle wire that is at x is equal to 0. We have another wire that is x equal to minus d, and the third wire which is at x is equal to d. Therefore, we say that the distance from a point x to each wire. So let us write that, let us consider, okay, so this is region 1 and this is our region 2, region 3, and we have region 4. So let us consider a point in region 3, and let us suppose that point is x. Okay. And so we consider a point along between region 3, and that point is suppose somewhere here, and this point is our x. Okay. And this distance is our d, so the total distance of this wire comes as d plus x, and from the next wire it comes as d minus x. So we can write that, and please remember this is our minus d, this is our plus d, and this point is our 0. You can say that to wire at minus d, distance is equal to x plus d, and this distance is our x. To wire at 0, distance is x, and Okay, here we can also write the direction of the field. So let me rewrite it again. At x is equal to x plus d, the magnetic field is our into the page. That is our minus z, and to wire at 0 we have a distance which is x, and field is our into the page, into the page, that is minus z. And finally we have third wire. You can say our two wire at plus d, the distance is d minus x, and here the field is out of the page, out of the page, that is plus z. Therefore we can say for the total field to be 0. For the total field to be 0, we can say that our, let us call this field as B1, and we have this as B2, and finally is our B3. You can say our B1 plus B2 should be equal to B3. Now we simply substitute the formula for that. I can write my B1 plus B2 is equal to B3. Substituting, we get our mu naught I upon 2 pi x plus d plus mu naught I 2 pi by x should be equal to mu naught I upon 2 pi d minus x. And mu naught I, mu naught I, mu naught I, 2 pi and 2 pi cancels out. So we are left with only 1 upon x plus t plus 1 upon x is equal to 1 upon d minus x. And if you solve this equation, we are going to get that our x is equal to plus minus d upon square root of 3. So this is your first part. Now we come to the part B. Part B, it says that the wire at the center is moved slightly. Okay. So we can just redraw the figure. So this is our x-axis, and we have two wires. One wire, the second one, sorry, this is third one. This is one wire, this is third wire, and the second wire is moved somewhere here, and this is our second wire. And this distance is our d. This distance is also our d. And we assume that this distance is of r and this is also r, and angle made here is our theta, other side is also our theta. And this is our, this is the basic figure for part B. And in this case, we can just explain the figure. So we have wire 1. This wire 1 is x is equal to minus t. So this is our wire 1 and this is our wire 3 and this is our wire 2, and then we have our wire 2, and this wire 2 is our central one and it is at x equal to 0 and it is displaced along z axis. Displaced along z axis, and we have our wire 3 and this is at x is equal to plus t, and the current they are carrying is in same direction. So all carry current in same direction, let us say into the page. So they are carrying current into the page. So this is basically the direction of the current. And we have to find out its SHM, whether it is going to execute SHM or not, wire 2 specifically. So for that we are going to find out the force between the wires. Magnetic force between the wires. And the magnetic force per unit length, magnetic force per unit length carrying a current I, separated by a distance r, we can write that our F is equal to mu naught upon 2 pi I square divided by r. And we can say if this distance is our x, then we can write that our r is equal to square, it is z direction, let me write it z. So this becomes r is equal to d square plus z square. So we can simply substitute the value of r, and we can say that force from each wire each of the wire 1 and 3 on wire 2 can write this as our F is equal to mu naught upon 2 pi I square divided by d square plus z square and its square root. And the force will be along this side. So this is our force F, and other side we are going to also have force F. And this force can be divided into two components. So let me draw the figure here. So we have wire 2 and we have force F. To the other side also we have a force F. Each force can be divided into two components, and we have this angle as theta. So we are going to this component, let us suppose, is our f of x, and the other component will be its, well, let me write in the, this will be our f sine of theta. In the downward direction we are going to f cos of theta, and for the other wire we are also going to have same. To the left we are going, to the right we are going to f sine of theta, and in the downward direction we are going to f cos of theta. So these two forces are equal and opposite. So therefore we can say that the x components cancel out and z component add up. Z component add up. Okay. And the z component will form as a net restoring force, and these will form net restoring force. Restoring force. So if we call this as our Fz, and we can write that component of net force, which is our Fz. So Fz will be equal to F cos of theta. So if two forces, this will be twice. We can substitute value of F. So this comes 2 into mu naught upon 2 pi I square upon square root of d square plus z square. Cos of theta will be our z upon and square root d square plus z square. And we can just simplify it. So this is our Fz net. So we get this as mu naught upon pi, and here we have I square z upon d square plus z square, because quite easily 2 and 2 cancels out, and this 2 becomes whole square and it cancels out. Okay. So it means this force acts towards z is equal to 0. This force acts towards z is equal to 0. So it's restoring force. And it is said that displacement is very small. So we can say for small displacement, this z is very much less than d, so we can say our d square plus z square is approximately equal to d square. This gives us that our fz net will be equal to approximately mu naught upon pi, and this is I square z upon d square. And as it is restoring, so we can write that our fz net will be our minus of mu naught I square upon pi d square multiplied by z. So obviously from here we can say that the restoring force is directly proportional to the negative of the displacement. And we also know that, or we can say the restoring force that is a F is equal to minus K times Z, and where K is our mu naught I square upon pi d square. Therefore, now we can find out the time period which we are supposed to find out, or frequency of oscillation, not time period. So we are given that the lambda is mass per unit length. Therefore, we can write our F is equal to lambda A, which gives us that minus kz is equal to our lambda A, and this gives us A will equal to minus k upon lambda multiplied by z. And we can further write it over A, which is a standard equation, is minus omega square z. This is for SHM. So therefore, our omega will be equal to k upon lambda. We already know k. We substitute the value. We get this as mu naught I square divided by pi lambda d square. And the frequency of oscillation that is a F is equal to omega upon 2 pi. We substitute the value of omega, we get F is equal to 1 upon 2 pi square root of mu naught I square divided by pi lambda d square. We can write this as I upon 2 pi d and square root of mu naught upon pi lambda. So this is the frequency of oscillations. We come to the next question, which was asked in the year 1996. And it says that an electron in the ground state of hydrogen atom is revolving in anti-clockwise direction in a circular orbit of radius r. Obtain an expression for the orbital magnetic moment of the electron. And part B, it says that atom is placed in a uniform magnetic field induction B such that normal to the plane of electron's orbit makes an angle 30 degree with the magnetic induction. Find the torque experienced by the orbiting electron. In this case, we are given that we have a electron, and that electron is in the ground state of the hydrogen atom and revolving in anti-clockwise direction. So in the first case, we have to find out the expression for the orbital magnetic moment of the electron. So this is a figure. This is the orbit, and the magnetic field, and we have a, you can say, making an angle of 30 degree with the magnetic field. So first of all, we are going to find out the magnetic moment of electron, and that electron is in the Bohr's ground state. You can say part A, magnetic moment of electron in Bohr's ground state. And ground state basically means that the value of n will be equal to 1. So we can write that your quantized angular momentum this gives us that our mvr is equal to h upon 2 pi. So we can write that our velocity v will be equal to h upon 2 pi m multiplied by r. So this is basically expression for the velocity, and from here we can find out the time period of revolution. Time period t of revolution, we can say our t is equal to 2 pi r divided by v. We substitute the value of v, we get this as 2 pi r, v is our h upon 2 pi m r. This gives us 4 pi square m r square and divided by h. So this is a time period, and because of the circular motion of the electron, we can find out the current. Say current due to electron motion. If that current is represented as I, so I will be equal to charge upon time period. Charge over E, time period is T, so we simply substitute value of time period we just calculated, and we get this as E upon, and T is our 4 pi square m r square whole divided by h, and this can be written as he divided by 4 pi square m r square. And the area of orbit is our pi r square. Area of orbit, let us suppose A, will be equal to our pi r square. So based on this, finally we can find out our magnetic moment, that is our current and A, area. You can say the magnetic moment that is a m will be equal to I a. We substitute value of I, which is our EH divided by 4 pi square m r square, and here we have pi r square, and pi r square cancels out. This goes with pi r square, so we are left with our magnetic moment will be equal to EH divided by 4 pi m. I think only this was asked in the first part. Orbital magnetic moment. Okay. And sometimes this is also called as also known as a Bohr magnetron. Okay. So we can say that this is also called as Bohr magneton. And represented as mu b. So mu b will be nothing other m, and that will be equal to EH upon 4 pi m. And if you want to find out direction, we can find out the direction according to right hand rule. So you can say that the direction of magnetic moment vector is perpendicular to the plane of electron's orbit, to the plane of the electron's orbit. So this was about the direction. We come to next part, that's part B. We are going to find out the torque on a magnetic dipole. I think this was asked, torque on a, if the atom is placed in uniform magnetic field induction B, find the torque experienced by the orbiting electron. Okay. So we come to the part B. We find out the torque on the magnetic dipole. Torque on magnetic dipole in a magnetic field, and it is given that the atom is placed in the magnetic field B, which is having a vector m, makes an angle 30 degree with the magnetic field. So we are given that the atom is placed in a magnetic field B, and magnetic moment vector which is our capital M, makes an angle 30 with the B, makes an angle of 30 degree with the magnetic field B. So we can write the standard formula of the torque. We can say our torque, that is our tau, is magnetic moment and magnetic field, and which can be written as our mb sine of theta. And we already know our m, So we can write our torque is equal to m is our EH upon 4 pi m, and here comes B, angle is 30 degree, which is 1 by 2. So therefore the torque will be equal to EHB, sine 30 is 1 by 2, so this comes as 8 pi m. So this is our torque, and the direction of the torque will be perpendicular to the plane formed by both m as well as b. So direction of torque is perpendicular, because of the cross product is perpendicular to the plane formed by magnetic moment and our magnetic field. And finally we come to our next question. In the next question it is said that we have it is asked in the year 1997, a proton, a deuteron and an alpha particle having the same kinetic energy are moving in circular trajectories in a constant magnetic field. If Rp, Rd and Rd denote respectively the radii of trajectory of these particles, then we have to find out which of this equation or A, B, C, D option is the correct one. And we start from the basic formula that the charged particle moving in the magnetic field, from there we can find out the radius directly. You can say charged particle in a magnetic field moving in a circle, radius r is our mv multiplied by charge and magnetic field. And we are given that they have the same kinetic energy. So we are given that they have same kinetic energy, and let us suppose it represented as k, which will equal to half m v square. So from here we can say our velocity v will be equal to 2k divided by mass m, and let me write this as equation number 1 and this is our equation number 2. So using the velocity equation in the radii equation, so we can say from using equation 2 in equation 1, we get our radius will be equal to divided by q, and numerator will be by m square root of 2k divided by m, which can be written as 2km square root upon q multiplied by b. So from here we can say our radii is proportional to m upon q, and we can divide this equation for each particle. You can say, let us call this equation number 3. Using equation 3 for each particle, and we are given deuteron, alpha particle, and a proton. So we say let MP and QP, these are the mass and charge on proton. Charge on proton. So based on this, we can write that mass of deuteron, that is called as MD, which will be equal to twice of MP, and charge on deuteron, let us call that as QD, will be equal to our QP. And finally, we can write for alpha particle also. We say mass of alpha particle is our M alpha, which is equal to 4 times mass of the proton, and charge on alpha particle, that is our Q alpha, is equal to twice charge on the proton. Similarly, we can write that for proton, radius of proton is directly proportional to square root of mass of proton divided by charge on proton. And we can write for deuteron, we have our radius of deuteron is proportional to twice mass of proton divided by charge on proton square root, and we can just modify it. This square root of 2, this becomes mass of proton divided by charge of proton, which will be equal to square root of 2, or we can say that our radius of deuteron will be equal to square root of 2 and radius of proton. And finally, for our alpha particle, so we have our alpha is directly proportional to 4 times mass of proton divided by twice charge on proton, and this gives us 2 mass of proton divided by 2 charge on proton. Here 2 and 2 cancels out, so we get our radius of alpha particle is equal to mass of proton divided by charge on proton, and this is equal to our radius of proton. So radius of alpha particle is equal to radius of proton. Therefore, the final answer, we can just make use of all the results, and we can say radius of alpha particle is equal to radius of proton, and which will be less than the radius of deuteron. So the option that's the correct one, you can say radius of alpha particle is equal to radius of proton. Option number A is the correct one. Option A is correct. So these were the questions that was asked in the year 1997. There were 2 questions for 1997 and 1 question for 1996. These complete all the questions. Thank you.